I'm Anuj, and you're watching the Applied AI Product Management course. I've been working in product management for over 6 years now. Most recently, I co-founded and successfully exited an AI B2B SaaS startup. In this video, I'll walk you through AI and machine learning fundamentals in the simplest way possible, while still helping you build a deep understanding of how these systems actually work. This video is part of a larger course I'm building on applied AI product management. This course is for people who are either thinking of entering AI product roles or transitioning from traditional product management into AI-driven products. Now, when I say applied AI PM, I'm not talking about product managers who are building foundational models or AI infrastructure, but who are using these AI models to solve real user or business problems. Here's how this video is structured. We'll start by clarifying what AI actually is. Then we'll go deeper into machine learning, understand how models learn from the data, how predictions are made, and how ML systems run in production. And finally, we'll talk about deep learning, what actually makes it different, why unlocked modern AI, and also discuss trade-offs it introduces from a product manager's perspective. Throughout the video, I'll keep connecting the concepts back to what matters for you as an applied AI PM, how to think about problems, data trade-offs, and real-world constraints. And as you're watching, I'd love to have your feedback. What was clear, what wasn't, and which parts helped you build intuition versus which parts felt confusing. So please feel free to share that in comments. All right, let's start with the most basic question. What exactly is AI? So, AI is a branch of computer science that focuses on creating systems that mimic human cognitive functions. Think of human cognitive functions like learning from experience or reasoning and solving problems, or perception like recognizing faces or understanding sound, or maybe understanding and generating language, right? Making decisions in uncertain situations, or even being creative, right? So AI is focused on the goal of mimicking these cognitive functions in machines or systems so that those systems are able to perform tasks that would typically require a human intelligence. Remember that when we say AI tries to mimic these functions, we don't mean that it does these in the same way that humans do. Okay. So AI systems use mathematical patterns and statistical learning to approximate these abilities, right? So, although AI, particularly generative AI, has exploded in the last 2 years or so, one thing to note is that this field has been around for more than 70 years now. The term artificial intelligence was coined back in 1960s, and early AI systems were mostly rule-based. Like think of like thousands of if-else statements that were programmed by engineers to achieve a very specific, narrowly defined objective, right? So these rule-based approaches were obviously limited because real-life scenarios are far too complex to capture through rules. Now, we have come a long way from there, and we have entered into the era of Gen AI, where systems learn patterns from like large amount of data sets. So instead of manually encoding knowledge, we let the system discover patterns directly from the data. So this shift from rules to learning was a major breakthrough behind AI systems that we interact today. Okay. Now let's look at some examples of AI applications. Let's talk about Alexa. So, when you actually talk to Alexa or Google Assistant, it is converting your speech to text first, then interpreting your intent, finding what right action it needs to take, and then finally generating a natural language response which you hear from the Alexa speaker, right? So, this is like an entire pipeline of multiple AI systems that is working seamlessly. When we talk about Netflix, whenever you open Netflix, you see a whole bunch of recommendations that pop up. So there is an AI layer that is analyzing your viewing patterns, comparing them to like millions of other users, and then predicting what you are most likely to enjoy. Uh, and moving on to self-driving cars like Waymo or some other company cars, those systems are constantly perceiving the world, like detecting where the pedestrians are, what is the input from the traffic light, what are the road signs, and then using all of this to make like real life driving decisions. Okay, so all of these systems are the AI applications that we have interacted with in some way or the other. And in fact, in our daily life also, like when you open Gmail, there is a spam filter in Gmail, right? Or when you use Instagram, there is a feed ranking. On Amazon, there is a product sorting. All of these are AI systems that are running in background. Now, there is something to notice here. Each of these examples that I've just talked about, these involve massive amounts of data and constant decision making. So that's exactly where modern AI applications excel, uh, which are basically these tasks that are repetitive and it's data heavy and they also require real-time intelligence. Now, there are many terms in the AI space that are getting used interchangeably, and it is very easy to get confused between these. So, and one of the major source of the confusion is that AI is more of an umbrella term. Not every AI system learns. Not every AI system is a neural network. Not every neural network is generative. So let's just break this down in one by one, cleanly, so that you are able to understand. So at the outermost layer, we have artificial intelligence. That is like broad field aiming to mimic human intelligence. This includes everything like rule-based systems, search algorithms, optimization methods, machine learning, deep learning, generative models, all of it. Okay. And moving on to machine learning is a subset of AI. So machine learning is about learning patterns in from the data. Like as the name suggests, it's machine plus learning, right? So instead of explicitly programming the behavior in ML, we give the system examples, and it discovers the underlying relationships. It powers things like spam detection that we just talked about on Gmail, pricing predictions, churn predictions, ranking systems, fraud detection. So there are a lot of use cases. Basically, any system that needs to learn from historical data, for example, the relationship between the email contents and whether it's a spam or not, that's machine learning. Now, deep learning is a specialized class of machine learning algorithms that use something called neural networks. So these neural networks are mathematical structures that are loosely inspired by how neurons work in the brain. This deep learning is extremely good at complex tasks like recognizing objects, understanding speech, and analyzing text. Okay. So most of the AI breakthrough from the last decade, right, computer vision, speech recognition, and rise of large language models, they come directly through deep learning. And this is a neural network based architecture that is very powerful because it can learn hierarchical representation. So there are layers in your neural network where your early layers learn like simple patterns, for example, edges, middle layers detect shapes, and then deep layers understand the objects and their meaning. So this the ability to build the concept layer by layer is what deep learning is why deep learning outperforms traditional ML on complex tasks. And finally, we have generative AI. This is the most popular uh, part or type of the AI uh, that is booming in the last 2 years. These are deep learning models only that don't just analyze the data, they generate the new data as well. So they can generate text, image, audio, video, code, and even the entire scenes now. Okay. So models like GPT, Gemini, Claude, Midjourney, all of these models live in this category. Okay. So that's our foundation. Okay. So now that we have clarified what AI is and how machine learning fits inside the broader AI landscape, let's zoom in and talk specifically about machine learning. Okay. Now, the goal here is to help you understand how ML systems actually work so you can design better products, ask better questions, and ultimately make better decisions. All right. So, what is machine learning? At the core, uh, basically, it is about learning patterns from the data, just like the name suggests, right? So, in traditional software, we tell the system exactly what to do. We have conditions like these if-else statements, which determines the behavior of your rule-based system. But in machine learning, instead of writing these rules, we give systems examples and ask it to figure out the rules on its own. Okay. So, to understand this better, let's take a very familiar example, which is spam detection in email. Okay. So, if we were to build a spam filter using like a rule-based system, we might write rules like if, let's say, this email contains certain words, like certain words that may hint that this is a spam email, or if it has too many links, or if the sender ID looks suspicious, then this email should be marked as spam. Okay, so those will be the set of rules that you would have to write. The problem is spammers adapt to these rules very quickly, and then these rules start to break in production. Now, machine learning approaches this differently. Instead of writing the rules, we show the system thousands of emails, and some of them are marked as spam, some are not, and that information is also given to the machine learning model. And the model learns the patterns that predict whether a new email is likely to be a spam or not. Okay. So when I say the system learns patterns, what it actually is doing is it looks at the signals inside an email. So we'll talk about that next. So think of this as like a normal email that comes, but now machine learning model is supposed to identify whether it is a spam or not. So uh, all of these things are signals that are coming. One is the subject of the email, what words were used inside the subject, then the repetition of the sender ID, the content that is there inside the email, and again, what are the words? Maybe some risky words were used over here, which uh, indicate that this could be a spam, and also the links that are present inside the email, right? So all of these things are signals inside each and every email, and your machine learning model looks into all of these signals along with the uh, way similar emails were treated in past. So whether this email was actually categorized as spam or not is also something that machine learning model takes into account. Okay. So each of these signals that are given to that give the system a hint about whether an email might be a spam. In machine learning, we call these signals as features. So this is feature one, two, and three, and four. Okay. And features are just numbers that represent some information that the model uses as an input to make predictions. Now, I also said that system is looking at how emails were treated in the past, right? For example, this one was a spam and this maybe the other one wasn't. These known answers or ground truth is called labels, right? So during training, labels are used to measure how close the model's prediction is to the correct answer. And then that helps the model optimize its training process and move towards a better accuracy. And this is a critical point for product managers also. So if the labels are wrong, inconsistent, or biased, the model will confidently learn the wrong thing. Okay. So we need to make sure that the input data that is going inside the model has the right labeling done. Okay. Now let's talk about what is actually doing the learning, which is the model, obviously. Now, at the concept level, model is just a mathematical function that learns the relationship between your features and labels. So imagine we had only three features in the email example that we talked before, right? So how many links it contains, whether the certain suspicious words appear, and the sender ID's past repetition. So the model combines these three different features into a simple mathematical formula. This is a linear relationship that the model is trying to establish. No, don't worry about these symbols. The idea is more important than notation here. So X1 could be the number of links. X2 could indicate whether certain words appear or not. And X3 could represent the sender ID's repetition. Each W that you see here, right? W1, W2, and W3 represents how important that feature is. Uh, how important, let's say, X1 is, how important W2 represents how important X2 is, and so on. And a higher weight means that the feature has more influence on the ultimate result that you get. B is nothing but a bias term. Think of it as a like a baseline adjustment that captures how spammy the word looks like before seeing any of the features, right? And now here's the key idea. The model doesn't know the appropriate weights or like biases or this bias in advance. So during training, it will start with random values. It will make a prediction, then it'll compare that prediction with the correct label. Let me show that here. Yeah. So during the training process, what will happen is uh, the model will start with random values for weights. It will make a prediction and it will compare the prediction with the correct label. And then it'll slightly adjust the weights to reduce the error and then repeat this entire process. So this is the learning part of machine learning. Okay. And this process repeats again and again until the adjusted values no longer meaningfully improve the performance on new unseen data. And the number produced by this formula that you just saw is just raw score. Okay. So by itself, this score doesn't mean spam or not spam. This is just raw score that is passed through another step that converts it into a probability, like a number between 0 and 1. For example, something like 87% chance that this email is spam. And at this point, the model's job is done. Finally, on the product side, you apply a threshold to decide what action to take. Okay. There's one important distinction to understand here. Everything we have talked about so far, like learning weights, adjusting them, improving over time, all of this happens during a phase called train. Okay, so this training happens on offline, and it happens on huge amounts of historical data, usually in batches. And once the model is trained, whenever a brand new email arrives, we simply run the trained model on once to get the prediction whether it is a spam or not. So this step is called inference. Okay, and training can take minutes, hours, or even days, right? However, inference usually needs to happen in milliseconds. Now we'll talk about machine learning pipeline next. So almost every machine learning system in production follows the similar high level flow. So it starts with data. For supervised learning, which is the type of learning that we were discussing related to spam detection, this data comes with labels. Like you have a labeled data set. That's what is the terminology that is used. Okay. Now we already know what we mean by labeled data set is that we already know which emails were spam and which weren't. And from this labeled data, we extract the features. Those features and labels together are used then to train the model. And once the model is trained, we evaluate how well it performs. Does it catch the spam? Does it block legitimate emails, maybe? Or how often does things go wrong, right? So if the performance look good or when the performance look good, your model is deployed. And now during the inference phase, the model start making prediction on new incoming emails. Okay. But the story doesn't end here. Over time, things change in the real world, like spam patterns change, your user behavior change. So you monitor the model, collect new data, retrain it periodically. So this creates a loop and uh, uh, and make sure that it stays relevant, right? So this loop of data training, inference, monitoring, and then retraining is what people mean when they talk about machine learning pipeline. Okay. Now, what does this mean for you as an applied AI product manager, right? So you might be thinking, um, like I'm not going to train models or I'm not going to tune weights. What do I do with all this GAN? Okay. So as an applied AI product manager, your job is not to build this model, obviously. Your job is to build the right system. And this requires a few things. First is framing the right problem. So uh, the first thing that you will need that ML needs is a very, very clear problem, right? So what exactly are you trying to predict? Whether it is spam or not spam, or maybe you are looking at figuring out the likelihood of churn of a particular user, or the probability of fraud, maybe the best item to show next. So the problem framing has to be uh, accurate and precise. Okay. Next is understanding the data. So the second thing that ML depends on is the data. So where does the data come from? How is it collected? How noisy it is? How biased it is? How often does it change? All of these questions are not engineering questions. These are product questions, right? So many a times ML systems fail because the data does not represent reality. Okay. And next is defining what good actually means. So this is the evaluation part. Accuracy alone almost accuracy alone is almost never enough. So blocking a legitimate email might be bad, or would definitely be bad. Letting spam through is also bad. Which is worse is something that you will have to figure out, right? And make sure that your thresholds are set in such a way that it is solving for the user, but also not creating a problem for the business, right? So all these decisions are again product decisions. As an AI product manager, you will have to decide the trade-offs, you'll have to decide the threshold, what is the acceptable failure rate, and how much uncertainty users can tolerate. Okay. Then next is designing for failure and not perfection. This is another important mind shift. Machine learning systems are never perfect. Like they will make mistakes. They will encounter edge cases. They will behave unexpectedly when the world changes. And it's not your job to eliminate failure, it's your job to design for it. So that means adding those confidence thresholds, having some sort of a fallback logic in place, allowing manual overrides, and maybe involving humans as well wherever needed. So the model will provide the intelligence, but your product needs to provide safety and control on top of it. And finally, need to think in life cycles and not launches. ML features are not built once and shipped, right? So they degrade over time, user behavior changes, and maybe even the business context changes. So you as a PM are responsible for the entire life cycle, which is launch, monitoring, feedback, retraining, and iteration, right? So these are some of the important things that you need to keep in mind as an applied AI product manager. Now, quickly covering the three different types of machine learning there is. And after this, we'll talk about deep learning. Okay. So first is supervised learning. This is something that we have been discussing so far, right? So we have data, we have labels as well along with the data, and the model learns to map the input to the known output. Okay. So spam detection, fraud detection, churn prediction, all of these things fall under this category, supervised learning. Then there is unsupervised learning. So here we don't have labels. The system looks for structure in the data, and and on its own it creates things like clusters, segments, or patterns, right? So this is often used for user segmentation or anomaly detection types of use cases. And lastly, there is reinforcement learning. Here the system learns by interacting with the environment, and on the basis of feedback that it gets from the environment, whether it is a reward or it is a penalty, right? The agent learns or tweaks its behavior accordingly. And this is commonly used in areas like recommendations, games, and robotics as well. Okay. So just knowing how these three different types of machine learning models differ would help you ask better questions later. So far we have talked about machine learning, and we have seen how models learn patterns from data, how features and labels work, and how ML systems run in production, right? Now, let's talk about deep learning. At a very high level, deep learning is just a subset of machine learning. But there is a fundamental shift of how the learning process happens. So to understand this shift, we'll again take a concrete example. In this case, we'll take an example of image recognition, face recognition from an image, actually. Okay. So imagine you're building a system that needs to accurately determine whether there's a human face in an image or not. Okay. Sounds pretty simple for humans, surprisingly hard for computers. So image is just a grid of pixels, right? And each pixel has it's each pixel is just a number. Like this pixel is represented by 249, 215, and 203. This is represented by another RGB code, and so on, right? There is no concept of eyes, nose, and face and all. It's all just numbers for the computer systems. So let's say if we were to build this with the help of traditional machine learning that we just talked about, we would have to manually define the features. Like in the email example, we saw that we can define features like how many, like the number of links that are there in a particular email, or presence of suspicious words, or the authority of the sender. All of these features were defined by somebody like us, and the model was told that these are the features that you need to consider. But uh, over here, uh, if we were to guess which features matter and then let the model figure out weights of those features, that will start breaking down very quickly, because images become very, very complex very easily, right? So if there is certain lighting changes, or if there are probably millions of types of faces that exist, all of these things will start breaking down your traditional ML model. And this is where deep learning takes a different approach. So instead of humans deciding what features matter, the model learns its own representations directly from the raw pixel data, right? So this is the key idea. So deep learning model uses something called a neural network. So despite the name suggests it is not a brain, and neural networks don't think the way human do. Remember, we talked about how AI, the field of AI is focused towards the goal of mimicking human cognitive functions, right? So, neural network is simply a stack of mathematical layers, and each layer is doing the same kind of weighted sum computation that we saw earlier, followed by something called a nonlinear transformation as well. Okay. So each layer takes in input and it applies weights. It adds a nonlinearity and then it passes the result forward to the next layer. Okay. And how do neural networks actually learn? So when a neural network sees an image, right, it runs the image forward through all its layers, and then it produces a prediction. Okay. Let me walk you through this. So it runs the image forward through all its layers, and then it produces a prediction. That prediction is then compared with the correct answer. For example, whether the image contained a human face or not, right? And the difference between the prediction and the correct answer is measured as error or loss function. Okay. This error is then sent back to the model. And based on this signal, the weights in each of these layers, right, in each of these layers is adjusted slightly. And weights that reduce error are strengthened. Weights that increase that this error or loss function is those weights get weakened. And this process repeats across thousands and millions of examples until the network learns representation and uh, consistently reduces error. So that's how feature learning actually happens. So none of these layers, so no layer is told what an edge is, or no layer is told what a face is, right? So the network simply learns whatever representations help it make better predictions. All right. So notice what changed here. We didn't tell the system what an eye looks like, or we didn't define what a face looks like. The model learned these representations on its own just by seeing enough labeled images. And this ability to automatically uh, learn these hierarchical representations is what made deep learning a breakthrough. And for a long time, this approach wasn't practical. Right? We didn't have enough data, or we didn't have enough compute or fast enough hardware. Once the larger data sets became available and GPU processing was made massively, GPUs made processing massively feasible, deep learning started at scale. Right. So this is why in the last decade we saw major jump in use cases like image recognition, speech recognition, and even language understanding. Now, before we move on, there are some trade-offs as well that we should discuss of deep learning. It is powerful, but it comes with some very real trade-offs. So these models actually need large amount of data, and they are very, very expensive to train, uh, extremely hard to interpret and debug, and they're also heavier at inference as well, which means that it impacts your latency and cost. This is something that will feel directly in your product metrics and in your infra bills, right? So as a product manager, it's important to understand that deep learning is not always the right choice. Sometimes simpler ML models are faster and even cheaper and easier to control, like for the example that we saw for spam filter, right? Now, where do LLMs fit? So, taking the same idea of learning representation in layers and applying it to text instead of image, that's primarily the intuition behind large language models. So, large language models are nothing but deep learning models that are trained on massive amounts of text to learn representation of language and also generate text probabilistically, right? So, the goal here is to figure out or predict the next best word uh, from the input. So if in case in this case the input were these words cat sat on A, and mat is the predicted word that we have got. Now once the LLM does this at a very good level of accuracy and does this again and again, you see those uh, AI chatbot use cases becoming possible, right? So when you are talking to ChatGPT, what is actually happening is on the basis of your query, the entire First, there's a layer of tokenization. So your entire input gets tokenized, and then that entire input goes into your neural network, which is like a large language model that is trained to predict the next best token or word. And once the next token comes, it repeats the process again to generate a coherent paragraph or sentence or a response for you. Okay, we'll go much deeper into this in the upcoming videos. For now, just think of LLMs as deep learning models applied to language, and we'll open this black box properly in the next video. All right. So, what should you take away from this? As an applied AI product manager, you don't need to know how neural networks are built or maintained, but you do need to understand why deep learning models behave the way it does, right? Why it needs large amount of data, why it needs huge compute, why it's powerful and unpredictable at the same time. Remember that deep learning gives you the capability, but it's the product design that will give you control, right? So far we have built the foundation. Now that you understand how AI systems learn, how machine learning works in practice, and how deep learning unlocks modern AI, most of the AI products that you see today, like chatbots, copilots, agents, all of those are largely powered by large language models. So in the next video, we'll open that black box. Thanks for watching.